Hello everyone. I know that the mechanics exam is coming up very soon, and so I want to quickly do this paper with you. So this is the latest paper. I don't have an official document yet, but it is the March 2025 paper 4-2. I haven't yet looked at it, so we are going to do it together. I hope that it can help you as you are doing some last prepping. Alright, so question 1 says 3 coplanar forces of magnitude 40, 30, and x act at a point in different directions shown. Given that the forces are in equilibrium, find the values of theta and x. And they've defined what theta is, they've given that to us, and then we can see that x is the magnitude of that force. Okay, so if you see forces are in equilibrium, that means that my sum of my forces in my x direction and the sum of my forces in the y direction equal 0. That is my strategy that I'm going to follow. So if we just look in the x direction now, I am going to take a look. So my x, that has a component in the x direction, and then my 40 is acting in the negative x direction. So I've just got negative 40 plus x, let me maybe write it a bit differently, x cos theta is equal to 0. So there's only two components in the x direction, and we end up with x cos theta is then equal to 40 if we take it to the other side. Okay, if I look at the sum of my forces in the y direction, they are also equal to 0. And in the y direction, I've only got 30 acting up, and I've got x sine theta acting down. So that's negative, minus x sine theta. If I then take my x sine theta to the other side, I haven't really taken it to the other side, but it says if I took it to the other side, x sine theta is equal to 30. Okay, so here I've got two unknowns, my x and my theta. I want to do a simultaneous equation between them, and there is a bit of a trick for this question, and you are allowed to do this. So x sine theta is equal to 30, and if I were to divide that by x cos theta is equal to 40, then what I end up with, my x's cancel out, and I get tan theta is basically 3 over 4. Now if we were to simplify that, we get a theta of 36.8 or 9 degrees. And then you can go back to either one of your equations. So I'm just going to go back to my x sine, and I'm going to make x the subject of the formula. And basically my x, I'm keeping the value in my calculator, so you never want to round off too soon. So I'm just saying 30 divided by sine, and then I'm going to recall my answer. And I get x is 50 newtons. Okay, so I do hope that little trick in between helped you. Another way that you could have done this, which is maybe a little bit more clean, is you could make x the subject of the formula, so that's cos theta, and here x is 30 over sine theta. Then when you equate the x's together, because they are the same, then you'll see that you end up in the same place. So you'll end up with tan theta is 3 over 4. So that might be a nicer, more official way to do it, but there is a bit of a shortcut if you want to do that. Okay. Let's go directly into question number 2. And every time I do these questions, I like to always orientate myself amongst the syllabus to know where am I, what am I doing. So before you even start the paper, you need to be comfortable that you know your mechanics syllabus. If I just give you the 5 main topics, we've got forces and equilibrium, and that's one that we just did now. Then you've also got kinematics. And there's a couple of branches that come out of this one. Then we've got momentum. Then there's one that they call Newton's laws. I'm just going to call it Newton's second law. because that's mainly the questions that we use in that topic. And then the last one is energy, work, and power. Okay, so you need to know where you are in the syllabus before you even start the questions. Okay, let's take a look at the next question. A cyclist is traveling along a straight horizontal road. Okay, this, if it's straight and horizontal, it doesn't have to be horizontal, but straight means you can use kinematics. Kinematics, it's kinematics of motion in a straight line. Okay, so that already gives us the tip that we are allowed to use kinematics. So a cyclist is traveling in a straight horizontal road at a speed of 4 meters per second when she passes point O. Okay, so it's not that she's staying the same speed the whole time. She accelerates at a constant rate. Okay, accelerating at a constant speed means a certain thing. So under kinematics, we've got constant acceleration and we've got varying acceleration. So under constant acceleration, we can use suvat. And we also often have our time graphs with straight lines. Under varying acceleration, we need to integrate or differentiate. Okay, so I hope this is helping you a little bit. Just navigate. So there's a constant acceleration for a distance of 42 meters. So I'm just going to jot down what I've got so far. So at point O, she's got a velocity of 4, or a speed of 4. She accelerates at a constant rate for a distance of 42 meters. Okay, reaching a speed of v. So her final speed is v. She maintains a speed of v for 50 meters and then decelerates before coming to rest. Okay, so what I'm seeing here is this is actually probably more like a time graph. So I'm going to just draw myself a time graph, because we can see she is accelerating for a certain amount, then she's going at a constant speed, and then she's decelerating before coming back to rest. Okay. The distance traveled while decelerating is 16 meters. Okay, let's just go and see what we can fill in. So a cyclist is traveling on a straight horizontal road at a speed of 4 meters per second when she passes a point. So she's already going at 4 meters per second. Okay, that's point O. She accelerates at a constant rate for a distance of 42 meters. Okay, so what you need to know about time graphs, where your acceleration, it can be constant or not constant, but what you need to know about a velocity time graph is that your area under the graph gives you your distance or your displacement, depending on how you look at the area. So the area under the graph gives you distance or displacement. Okay, then the gradient of the graph, I hope you know what that is. Gradient gives you acceleration. Okay, acceleration, and if it's going down, deceleration. Okay, so if she's going for a distance of 42 meters, that means this area over here is 42. Okay, it feels a bit funny saying 42 meters, so the area is just 42. Let's leave it like that. Reaching a speed of v. Okay, she maintains a speed of v for 50 meters. Okay, so the area under this rectangle is going to be 50 meters, and it's a constant speed. Okay, so the area under this is 50 for a constant speed, and then the last one is she decelerates, and they've given us the deceleration before coming to rest. Okay. And that's the distance that she moves is 16 meters. Find the value of v. Okay. Let's see if we can set up a couple of equations here, and I'm sure we've got enough information to be able to figure this out. So the first pink part is a trapezium that we have. So I encourage you, instead of breaking it up between a triangle and a rectangle, let's just look at the trapezium. So you've got two different lengths. The one is 4 and the one is V. We want the average length of the trapezium, so you can divide it by 2, and we are timesing it by our height. Let's just call that T1. Now this is equal to 42 meters. Did she tell us any time? Okay, we don't know what the time is of that, so there's going to be a couple of unknowns here. Okay, if I were to just multiply my 2 to the other side, okay, I'm going to just leave it like that for now. I'm going to set up another equation. So my middle block has an area of 50. So that has a length of V. So it's my one side here, V, and another length, which we don't know what that is. V times, let's say this is T2, so it's going to be T2 minus T1, and that is equal to 50. Okay, so we're setting up a bunch of simultaneous equations here. Alright, and then my last section, so you might be able to see that I don't always know where to start, but I just need to start somewhere. Okay, my last section, let's make it blue. I've got a triangle, so my area is a half base times height. My base, we'll say, is T3 minus T2, and my height is V, and this is equal to 16. Okay, now they've also given us acceleration here, so I'm going to set up another equation with acceleration, and I hope that's going to help unlock a couple of things here. So my acceleration is 2. So my acceleration is my change in velocity divided by change in time. So if you were looking at just a normal straight line graph, it would be change in y over change in x, but now it's change in v over change in t. So we've got a velocity. I'm going to go from this point here. So v minus 0, that's my other point, is going to be equal to t2 minus t3, and we know that answer is 2. Okay, so let's see if I can solve any of this. Minus t3 is equal to v. Okay, I'm going to pop that v into this equation first. So 16. I'm just going to multiply that 2 up to the other side. Multiplied by v, which in this case is 2. Okay, that's looking very interesting. I'm actually going to rather do this a little bit differently here. I think this is going to be easier. Instead of saying T3 minus T2, I'm just going to label this over here as, let's say that's T. Okay, so here we've got a half times my base times my height is V. Now I'm going to replace my V with T times 2T. This is going to be much easier. Let's just go back to my 16. So the 2 and the half cancel out, and my t becomes t squared. So my t is going to be plus or minus 4. Okay, in this case we can see the time has gone 4 units across. So that actually helped me quite a lot there. So there's 4 seconds between those 2 points over there. Okay, if there's 4 seconds, I should be able to work out my v now. So my v is 2 times 4, which is 8 meters per second. Okay, so that was actually quite simple as soon as I did that little trick there. Okay, so I didn't even need the first few equations, I just needed those last 2. Alright, but what I want to show you is I don't know all the answers, I don't know where to start, but I know the principles. So just, you keep going. If you feel like you're getting stuck, just take a deep breath and try a different method. Okay. Alright, let's go to the next one here. So find the total time for which she's in motion from the instant that she passes O. The total time. Okay, so we've got a speed of 8 over there. We know the last little bit is 4. And we are actually going to use our other 2 sums now. Let's just take them both down here, which I can do on an iPad. It's not so easy otherwise. We already know that the V is 8. So let's go over here, 4 plus 8. Okay, 84 divided by 12 is just 7 seconds. Okay, so this first little part over here was 7. That means that's going to be 7 over there. And then the last part, the 50 meters, is going to be 8. And then it was t2 minus 7. And that's going to give us 13.25. But we mustn't actually forget this is our T2 value. So our T2 is this part over there. So that's 13.25, which is now already included the 7. So our total time is then just going to be the 13.25 plus 4. That's what we already worked out, and I think that's 17.25. So you didn't have to work out the T2 separately. You could have just worked out the change in time. But that's a good point. Just make sure that you do know which one you've done, so that you don't get confused. So if I were to do this again, I might just approach it differently, but often I'm just going, all the thoughts are going through my head, so I'm just sharing it with you as I'm going. Yeah, so it might not have been the cleanest method, but we got there. Okay, let's take a look at our third question. So here we have an aeroplane flying at a constant speed. Okay, I haven't seen an aeroplane before in a mechanics paper, so that's quite cool. There's an aeroplane flying at a constant speed. So constant speed tells you that you can use your formula. V is displacement over time, or distance over time. The only time you're allowed to use this particular formula is if you've got a constant velocity or speed. You may not use it if you've got any acceleration. Okay, then we're using suvat, or we got to use differentiation and integration. Okay, the airplane is flying horizontally. Okay, so it's also in a straight line. The airplane's engines are producing a constant power. So we jumped into the power chapter. Power, whenever you see power, there's 2 formulas, work done divided by time, or force times velocity. Okay, this force times velocity, you can only use this if it's a constant velocity or at an instant. So let's just write that down. Okay, so you do need to know each and every one of these things. What is the trick? When are you allowed to use it? When are you not allowed to use it? Okay, the airplane experiences a constant resistance force of that much. So I'm just going to draw my plane. I don't know if I can draw the best plane here, but it's producing a constant power, so my driving force is power over velocity. It's got a constant power 5500,000 watts divided by my velocity, and it experiences a constant resistance force of 25,000. Okay, that's friction. Find the speed of the aeroplane. Okay, so it's going at a constant speed, so the sum of the forces in my direction of motion is equal to 0. So all it has is 25,000 going backwards, and then it's got the driving force going forwards. Driving force is power divided by velocity, and that should be equal to 0. There's no acceleration. Okay, if we were now to solve for velocity, 25,000, I'm going to take my v up to the other side. And then if I divide through, so now we'll just make sure we get all the right number of zeros. Our velocity is then 220 meters per second. Okay, and that's interesting. It's hard to check because it's an unfamiliar concept of how fast does an aeroplane go. I haven't seen that in many papers, so it might make you feel uncomfortable in your exam. Just make sure you've got all the correct zeros and keep sticking to your principles. Okay, the aeroplane then ascends 300 meters in 50 seconds. Okay, so it's going up. Okay. Okay, it ascends 300 meters. Let's just draw my airplane in 50 seconds while maintaining the same speed. But it's going up now, which means it's acting against gravity. Okay, maybe I should have actually drawn my little airplane like this now. Okay, so it's going up. And now we've got friction and we've got mg sine theta coming down. Okay. The resistance force is no longer constant. Okay, so we cannot use constant. We've got to work now with probably mg. The work done against the friction when ascending 300 meters. So they've given us work done. And it's that many kilojoules. So we've got to add another 3 zeros. Okay, the mass of the aeroplane is 60,000. Find the average power. Okay, so remember when I told you about this formula, I said you can only use it if it's constant. Okay, constant velocity. And I guess it's constant power as well. So now it's not a constant power. So we're going to be working here with an average. So we're going to be working with work done divided by time. Okay. Okay, find the average power of the plane's engines. Okay. Alright, so this is an energy question. What's happening is the plane is going up, so there's a change in potential energy. So there's a change in potential energy, it's going up. I've got a little formula that I give my students. Anything going down goes on the left hand side, the change in EP going down, plus your kinetic energy initially, plus your work done by the engine is equal to your EP going up, plus your final kinetic energy, plus your work done by friction. Okay, so this is the general formula. In this case, there's nothing going down. The plane is going up. It does have a velocity to start with, so we're going to use that. The engine is going to be working, so we're going to be using that. It is going up. It's got a final speed, and there is friction. Let's just see here though, it says it maintains the same speed. So because it maintains the same speed, I'm actually going to take velocity out because it's going to be the same before and after. So our little formula is only work done by the engine and that is your change in your potential energy to make it go up, plus your work done by the frictional force. Okay, so big note to self here, make sure your zeros, you've got enough zeros, and the correct zeros all in the right place. So we want to work out the average power of the engine's plane. So this is what we are trying to, well, if we work out the work done, we can then get to power. Okay, so let's just start with work done by the engine. Is my change of my potential energy. So that's mgh plus, and they've given us this value here, 270,000,000. Okay, how much does this have to go up? Let's just see. So it's 300 meters, and it's taking 50 seconds. So how much is that going up vertically? Let's see. I think we are going to have to use a Suvat equation here. The plane ascends 300 meters in 50 seconds while maintaining the same speed. Oh. Okay, so the plane ascends 300 meters. So this might actually, that's a good question now. This is making me wonder, is it 300 meters here? Or is it 300 meters up the slope? Okay, we're not going to have to do Suvat. I think it's just ascending 300 meters. Okay, so that means I've got my mass, and then the time is going to be for my work done, my power calc. You see what I mean? Okay, so 60,000, 10, and my height is just, it's going up by 300 meters. And let's see what this gives us. So 60,000 times 10 times 300 plus 270,000,000. Okay, this is giving me 450. Ooh, there's so many zeros here. 1, 2, 3, 4, 5, 6, 7. Okay, that's the work done. So now power is work done divided by time, and so this is where the time comes in. So now my puzzle pieces make a bit more sense. So it's all of these zeros and divided by my time of 50 seconds. And that gives me 9 million, 1, 2, 3, 4, 5, 6, 9 million watts. And the question asked for the average power, so you could give it in kilowatts or watts. I'm just going to leave it, I think, in watts for this sake of there's no specific reason why. Okay, 9 million watts, and that is the correct answer. Okay, so this one also took me a little bit of time to figure out what is going on here. Once again, I just want to show you my thoughts. The first time I've ever seen the question, that's what happened in my brain. So it is okay if you maybe start going down the wrong path, then, you know, you're correcting yourself. And I realized, oh, okay, right, it's just ascending vertically 300, and then my time is going to be used for my power calculation. Okay, I hope this formula over here helps you. I do find this tremendously helpful, especially with energy and connected particles. If you can just figure out what's going up, what's going down, what's moving, and then driving force and friction. Okay, let's quickly take a look at question 4. Okay, question 4 says two particles, A and B, have a mass of 0.3 and 0.1. So first thing I'm trying to do is figure out which direction this would go in, and it's obviously going to go to the heavier side, 0.3. The particles are attached to the ends of a light and extendable string. The string passes over a smooth pulley, a fixed smooth pulley. The particles hang vertically below the pulley. Both particles are initially at a height of x meters above the horizontal ground. Okay, see the diagram. The system is released from rest. Okay, so this looks like a very typical connected particle question. Find the tension in the string and the acceleration of the particles. Very, very typical. We are looking at Newton's laws over here, specifically connected particles. And because they're looking for acceleration and tension, I'm just going to do simultaneous equations between them. So what does that mean? It means I draw a free body diagram of each particle. So particle A has got gravity pulling it down, which is 3 newtons, and it's got tension pulling it up. The system is going down, so down is positive. So my sum of my forces is mass times acceleration. So I've got 3 minus t is 0.3a. Okay, in this case, I'm just going to make tension the subject of the formula. And that is equal to 3 minus 0.3a. Then if we look at particle B has tension pulling it up and its weight pulling it down, which in this case is just 1 Newton. Now for B, up is positive. We always want the direction of motion to be positive. You can do it differently, but it's really just the easiest. Okay, so here we've got tension minus 1 is 0.1a. And that means tension is 0.1a plus 1. Two equations, we can put them together. So 3 minus 0.3a plus 1. If I take my like terms to each side, I've got 2 is equal to 0.4a. So a must be equal to 5. 5 meters per second squared. Okay, so that is my acceleration, and then I can just find out my tension by plugging it into either one of my equations. 0.1 times 5 is going to be 0.5 plus 1 is 1.5 Newton. This is a very typical connected particle question. So do make sure, if you're struggling with that, do make sure you practice loads of them. You always want to know which direction the system is moving. Take the direction of motion to be positive. And then we split up our particles, we draw free body diagrams, and we do simultaneous equations. Okay. Now, during the subsequent motion, B does not reach the pulley. Okay, so B is going up, it doesn't reach the pulley. When A reaches the ground, it comes to rest. Given that the greatest height of B above the ground is 1.2, ooh, this is interesting. Find the value of X. Okay, so this is typical, but asked very differently. So what normally happens is the system, when A hits the ground, so B would have gone up, and then it would have jumps. It jumps. So once A hits the ground, the rope becomes slack, B just does a little jump and then falls down again. Okay? Let's maybe just show that differently. It's going to do a little jump like this. And they're saying the highest height above the ground is 1.2 meters. Okay, so all the way above the ground, this is 1.2 meters. Now they want us to find the value of X. Okay, so normally they give us X and then they ask us to find the highest value above the ground. Now they're just working it backwards. So that's okay, we can do all of this. First of all, okay, what we can see here is that is X there. This, as it travels with A, it's also going to be going a distance of X, so it's 2X. And then we've got to work out what the little jump is. So if we can work out the jump, we'll be able to work out the X. Okay, how do we work out the jump? First thing that we have to do is we have to work out what speed is this particle traveling at right over there. So it's starting from rest. Okay, it's going a distance of X. It's accelerating at 5 meters per second. and we want to know the final velocity. Okay, so this is suvat. So S is x, A is 5. Now it looks like we're going to be working in terms of x. We want to find out our v, and we know our u is 0. So v squared is u squared plus 2as. You can also do this with energy, by the way. Equals 2 times 5 times x. So our v is just going to be the root of 10x. Okay, root of 10x. Let's do this. Okay, so this v over here is root of 10x. So now it's going to start a little jump. So where this one ends, our new equation starts. And the speed at that point is the same speed, root 10x. Up at the top here, it's 0. Our distance, okay, so our acceleration is going to be gravity, minus 10. And this is interesting now. What is our distance going to be? If the total distance is 1.2 meters, it's going to be 1.2 meters minus 2x. I don't know if you can see that. So if you take away these two x's over here, that's what it's going to leave us with. 1.2 minus 2x. Okay, this is such an interesting question. Always draw your questions. Okay, so our distance is 1.2 meters minus 2x. Our u is root 10x, our v is 0, and our a is minus 10. Okay, and now we're working again. V squared is u squared minus 2as. Okay, our u squared is root 10x squared, so it's just 10x. Our acceleration is minus 10 squared plus 2as, so minus 10. And our distance. Okay, this looks solvable. Let's try it. I'm just going to say minus 20. Oh, I should do this without a calculator. Okay, this is still equal to 0, so 50x is equal to 24. So our x is 0.48 meters, and that is correct. So that's really cool to know that. Okay, so this is a typical question, except normally they ask you to find the height. Now they've given you the greatest height, and you've got to work backwards to find the starting height. So interesting. Always just draw your scenarios, draw your scenarios, draw your scenarios. The principles were the same, but it does take a little bit of figuring out the scenarios. Okay. Question 5. Immediately, this question makes me think of momentum, just by looking at it. But I can also spot the word collision there. Let's see what they have to say. So, 3 particles, P, Q, and R, of mass 0.6, 0.4, and 0.8 respectively, are traced in a straight line on a smooth horizontal plane. Okay, this is wonderful news. It's smooth. Okay, the distance from P to Q is 3 meters, and the distance from Q to R is also 3 meters. P is projected directly towards Q with a speed of 3 meters per second. Okay, P is projected towards Q. After P and Q collide, P continues to move in the same direction. So P is also going to be going in this direction, and Q. And this is going at 1.5 meters per second. Find the speed of Q after the collision. Okay, it's a 2-mark question. Super simple, super straightforward. We're in the topic of momentum. M1, U1. Okay, so our masses, always make sure you just got the right mass. It's 3 meters per second plus 0, so Q is not moving. 0.6, it's going at a speed of 1.5, and then 0.4 V. Everything's going to be going kind of to the right, although we don't like to say right and left, but it's going in the same direction as it started. Okay, V is equal to 9 over 4. If I plug that into my calculator, it is 2.25 meters per second. Okay, straightforward momentum question. Always look out for your direction. Okay. In the subsequent motion, in the subsequent collision, between Q and R, these particles coalesce. Find the speed of the combined particles after the collision. 1 mark question. Okay. So there's not a trick here. Q is now moving at 2.25. So Q is going at 2.25. R is stationary. P is kind of following it at 1.5, which is probably going to be necessary in our next question. Alright. For now, I'm just looking at Q and R. Find the speed of the combined particles after their collision. Oh, this is coalescing, so it's M1 plus M2 V. Q is 0.4. That's 0.8. And that means our velocity, 0.4 times 2.25. Our velocity of this particle .4 times 2.25 divided by 0.4 plus 0.8. I accidentally said multiplied by 0.8. So 0.75 meters per second. Okay, so it is the combined particles now moving at 0.75 meters per second. Okay, find the time that it takes from when P is initially projected, so the very beginning P was projected, until the instant at which P collides with the combined particles. Okay, so my trick for this is we're going to be using time stamps. Time is going to help us to keep track of everything and compare the particles to each other. Okay, so we're going from the very beginning until P collides again. Alright, so let's just look way at the beginning. P is moving at 3 meters per second towards Q, and it's 3 meters. Okay, and it's moving at 3 meters per second, so it's going to take a second. Okay, but let's write that down on paper. Okay, so P and it's moving 3 meters. Okay, so it takes 1 second for P to hit Q. Okay, now Q is going to hit R, and it is moving at 2.25 meters per second, and it's got to go 3 meters. So Q 2.25, and it's going 3 meters. The only reason we can use this formula is because it's smooth, it's constant. Okay, don't use it normally. Sorry, this T should be 3 divided by 2.25. And that's going to give us 1.333 seconds. Okay, So Q bumps into R and it takes 1.333 seconds. I'm actually going to write that as just 4/3 because then we're going to keep all of our decimals intact. Okay, 4/3 seconds. Now, because we want to picture this, I want to know where is P when Q hit R. Okay, so Q is colliding with R. Where is P at that time? So P is still moving. After the collision, hold on, it's not moving at the same speed. After the collision, it moves at 1.5. We don't know how far it is. I want to know where it is. And I want to know where is it when Q collides. So we're doing, every time there's something that happens, that's where we try and figure out where all our particles are at. Okay, so the next big thing that happened was there was a collision after 4/3 seconds. So I want to know where is P after 4/3 seconds. And it has moved 2 meters. Okay, so if I draw a little picture, Q and R have now collided and coalesced. And P has moved 2 meters forwards, which means there's just 1 meter between them. Okay. So now, after the collision, these particles are moving at 0.75. And this one is still moving at 1.5, I believe. Okay, so now where are these guys going to collide? Can you see that the combined ones are slower than P? So P is going to catch it up somewhere. So I always tell my students, let's bring in the X. Let's assume these guys are traveling X. What distance must P travel in order for it to collide? Let's say it's going to collide somewhere here. So this P has to travel. You have to work out how far it has to travel. Don't look at the position relative to each other. Look at how far the particle has to travel, because that's what goes in the Suvart equation. So this is x plus 1. Okay, so P, the velocity is 1.5, the distance is x plus 1, and we don't know the time. But the time that they're going, it's going to be the same time. So let me actually make that t. Okay, simultaneous equations, or let's first actually set them up. So 1.5. Okay. Oh, I've done something funny here. I should have made t the subject of my formula, not x. Hold on. Let's quickly rearrange this. Distance divided by time. Sorry. So my time I thought that looked a bit funny because I couldn't solve now, and that's not the way it should be. Okay, so I'm going to cross multiply here, and I can see that's not the lowest common denominator, but it's fine. I'm just going to do it anyway. Okay, I'm going to take my x's actually to the right hand side, so it's 1.5 minus 0.75, which should be 0.75. And therefore x is equal to 1. Okay, so x is equal to 1, so they're colliding in 1 meter, so my time is going to be x 1 divided by 0.75, which is another 4/3. Okay, so let's try and keep track of all of our times. So we've got our first time when P was going to Q, that was 1 second. Then when Q collided with R, that was 4/3. And we just worked out where was P at that time. But then it took P and the coalesced particles, it took another 4/3. So our total time is 1 plus 4/3 plus 4/3. And if we just take a look at that, I'm just going to make this 3/3. And that's 11/3 seconds. Then we don't need a calculator. This is an exact value, and that's great. You can do it like that. You can also put, you can work out decimal, but Cambridge does tend to like exact values, so maybe just leave it like this. Okay. Let's take a look. We've got 2 questions left. Okay, let's keep going. So here we have a block of mass 12 kgs on a rough plane. Okay, rough, as soon as you hear that, you know that there's friction involved. Okay, friction is mu times r. Inclined at alpha, where they give us alpha. Okay, tan, the inverse of tan of 0.5 is alpha. Force of x is applied to the block directly up the plane. The coefficient of friction between the block and the plane is mu. Okay, so they've given us mu, and they've given us 20. Find the time it takes for the block to move 2 meters down the plane from rest. Okay, interesting. So even though x is pulling it up, it looks like it's still going to be too heavy, and it's going to move down. So this is 120 newtons going down. So down the slope is 120 sine alpha. So I just want to see my sum of my forces in the x direction is mass times acceleration. So minus 120 sine alpha, which is inverse of tan. 120 minus 120 sine alpha. Okay, there is friction. So friction in this case is going to be acting up. This is going in the positive direction. Sorry, it's going down. Minus friction minus x is mass times acceleration. Okay, let's fill in a bit more unknowns. I can actually work this out quickly. 120 times sine of the inverse of tan of 0.5. That's not a nice number. I'm going to keep that in my calculator because I don't like it. Mu is 0.15. My R value is 120 cos of alpha. And then x is 20. My mass is 12. Okay, so I've got that. I'm going to put this all in my calculator. Okay, so that we find our acceleration. Simple, even though it just looks complicated. Okay, find the time that it takes the block to move 2 meters down, starting from rest. So U starts from rest. We want the time. We've got the distance of 2 meters, and the acceleration is now 1.46. So this is 1.65 seconds. Cool. Good. That's all that they're looking for. Not actually too complicated for a 6-mark question. It's not too bad. If you would like to work out these separately, so work out your frictional force separately, work out your gravitational force separately, but then obviously also try and put it into Newton, because that will be a method mark. Okay, it is given instead that the coefficient of friction is not 0.15. Okay, and that when x is equal to 10, okay, so now 10 is less. It's got less of a force pulling it up. It's probably wanting to go down still. The block is at the point of moving down the plane. Okay, so the point of moving down the plane. That means that the friction must be much higher than 0.15. Find the value of mu and find the value of x for which the block is on the point of moving up the plane. Oh, I love it. They just love to ask all these questions. Okay, what is the difference here? Difference is your friction. Okay, if it's on the verge of moving down the plane, it means your friction acts up. Okay? If it's on the verge of moving up the plane, it means your friction acts down. And that's going to give us 2 different answers. So let's look at the first one. So this is x is equal to 10. So my sum of my forces, in this case, is actually equal to 0. So minus 120 we are going to take, I'm actually going to take down as positive because it wants to go down. So minus friction was that the right 0.5 minus mu times r. This time we don't know mu. The only unknown here is mu, so we're going to work out mu. Okay, I'm just going to work out my 120 times sine of the inverse of tan of 0.5 minus 10 and this is cos of the inverse tan of 0.5 This does not look right. My mu is 48. Okay, right. So now if you're in an exam and you see a mu of 48, you've got to realize something's not right. Okay, mu can't be 48. Mu's got to be, it's normally between 0 and 1. If it is, it can be just over 1, but it's not much more than that. I don't think I've ever even seen it get to 2. Okay, so now I've done something wrong. Let's try and find what did we do wrong. So it is instead given that mu is not 0.15. Oh, I think I understand what I did wrong. This should be times 120 here. My R value is 120 cos of tan. Okay, times 120 over here. So if we just technically divide this by 120, we should get our mu. Don't do this in an exam. I mean, if you do it in an exam, rewrite it. Don't do what I'm doing now. Okay, so there we've got our mu value, and that's not the end of the question. They want to know, okay, so find the value of mu, find the value of x for which the block is on the point of moving up the plane. So now obviously x is going to be different, but friction is going to be acting down. So minus my 120 mg sine theta minus my mu times my r minus my friction minus my gravity plus my x should be equal to 0. And the only thing that we have to solve for here is x. So I'm going to do this on my calculator. I'm going to take everything to the other side. I've already got mu in my calculator. So I'm just going to say times 120 times cos of tan of 0.5. Okay, and I'm now picturing that on the other side of my equation. So then I'm going to add 120 times sine of the inverse of tan. I hope I did the inverse of tan previously. Okay, my x is 97.33 newtons, 3 significant figures. It's 97.3 newton. Oh, 97, oh my goodness. Okay. And I do believe that's also correct. Alright, so trick for this one. There's a lot of forces that keep it in equilibrium if there's friction. If it's slipping up or slipping down, the thing that's changing is the frictional force jumps from side to side. Okay, let's try do this last question. A particle moves in a straight line. So the only topic they haven't tested yet is the integration and differentiation. That falls under kinematics, so you have to have a particle moving in a straight line. Here, and this is, I can just see this is what it's going to be. So let's go. Particle moves in a straight line, the velocity of v. Particle t after leaving a fixed point is given by that. Okay, so we can see this is not a straight line formula. So this is varying velocity. K and p are constants. The acceleration at t is equal to 1 is that. The displacement, okay, so they've given us a point in time for acceleration, and then they've given us a point in time for displacement. Show that k is that and that and that. Okay, simultaneous equations. Alright, the first thing we have to do to get to acceleration, so here we've got our SVA. So when we go down, we differentiate, and when we go up, we integrate. Okay, so I'm gonna differentiate first. I'm just going to differentiate the inside. Forget about the k. So the 20 falls away. That becomes p minus 12t. Okay, maybe another way to do this, which might make a bit more sense, because you wouldn't know necessarily just to put the k out of nowhere. pkt minus 6kt squared. Okay, so we are differentiating t. Not p, not k. So this falls away. Here we've just got pk left, and this we've got minus 12 kt. Okay, they gave us a point in time for acceleration when t is 1, acceleration is 42. That's 1. Okay, I'm just going to leave it like that for now. Let's go to displacement. Here I am going to just take out my k. Okay, so I'm integrating. So it's 20t plus bt squared over 2. All of them need to be multiplied by k. Okay, when I am at a distance of 93, the time is 1 second. Okay, I've left out my ones there. Alright, now we've got to do simultaneous equations between these two. They like to make things complicated, I can see that. Okay, I'm just going to get rid of my fraction. I don't like having a divide by 2. That just isn't great, so I'm multiplying everything by 2. Oh, I've got to multiply that by 2 as well. 18 times 2 is 36. Okay, and over here, okay, I think I'm going to make pk the subject of the formula. It's a bit random, but it will help me to get rid of a variable. So this is equal to 42 plus 12k, and in this side, it's 186 minus 36k. So long as you're eliminating a variable, you could do this. I generally just try and look for the easiest route. Don't want to do too much work. 36 plus 12. K is equal to 3. Okay, if I then plug P3 186 minus 36 times 3. I get an answer of 26. Okay, that is pretty cool. That's what they asked me to show, so that's perfect. Okay, last question in the books. Find the distance moved by the particle between the time at which the acceleration is 0 and the time at which its velocity is 0. Okay, when I look at this, it looks super random, but we just have to stick to what it says. Okay, so acceleration, my acceleration formula is this one. Hold on. Ooh, be careful. This is still velocity over here. Okay, my acceleration is this one. So I'm just going to take it down. Okay, and in this case we know our P and our K. What's our P and our K? 3 times 26 is 78. 12 times 3 is 36. Okay, find the distance the particle moves between the time when the acceleration is 0. So let's make the acceleration 0. So 78 divided by 36 is just 2.166, but I'm going to leave it as 13 over 6. So we've got to go from that point in time, where the acceleration is 0, to where the velocity is 0. So velocity, I'm going to use my velocity formula. And here we know that K is 3 and P is 26. That is equal to 0. I'm going to divide 3 by 3. I'm also going to divide through by 2. I like to just keep my quadratics as simple as possible. This is a quadratic. Let's solve for it. So I might also divide through by a minus, actually. Let's hope this simplifies. 11, 6. Okay, this seems to work. Okay, always double check. Double check. So I'm just double checking in my head there. So time is minus 2 over 3, or time is equal to 5. Okay, so it must be 5 because we can't get a negative time. Okay, so we're going between our 2 time points, this one and this one. Okay, find the distance the particle moved. Distance, that word is very important, means whatever our velocity time graph looks like. Where was our velocity 0? That was only at negative something and 5. It's always important to know where it crosses the graph. And acceleration was 0 at 13 over 2. So I don't know what this looks like, but it could be going... Let me actually just quickly take a look. What does our velocity time graph look like? Okay, if you take a look at the shape of our velocity graph, you can see that this is a quadratic. And it's a unhappy face quadratic. So I'm just going to draw something like, probably looks something like that. So we are going from this time point over here where our acceleration is 0, 13 over 6, and 5. So all we have to do is integrate our velocity time graph between those 2 points. (13/6 and 5) of our velocity time graph. And we are doing it in terms of t. I am just going to multiply my 3 in. Actually, I'm going to take it out. I'm going to put on the outside, so it's 20t plus 26t squared over 2. And this should actually be just written like that, because I've already integrated now. I am putting 5 into everything. And let's see what this gives us. what is going on now? 20 times 5 plus 13 times 5 squared. My two numbers are just very different from each other, so I just want to check it. Sorry, this is not this amount. Times 3. 525. And then the other one, sorry, the one is in the thousands, the one's in the hundreds, so that was a bit of a check for me. 13 over 6 plus 13 times 13 over 6 squared to the power of 3, and everything is multiplied by 3. This gives me an answer of 272.9. Total distance of 273 meters. Okay, we've taken just over a minute to do the paper, obviously with different explaining in between. I hope that helps. Excuse me, I feel like I was a bit tired towards the end of the video, but I do hope that it's helped you tremendously. My biggest encouragement is make sure you know your way through your syllabus, through your mind map. Understand each formula, when you can use it, what are the tricks, and then work as fast as possible. Okay, all the best for the upcoming mechanics exam. I'm going to say goodbye.